Welcome aboard, future pilots. I am absolutely thrilled to have you here today. We're tackling a massive, incredibly important topic in this explainer: navigation systems and radar services. Whether you're just starting out, aiming for that private pilot certificate, or you're deep into prepping for advanced instrument ratings, understanding exactly how to navigate the skies and interact with air traffic control is the absolute bedrock of safe flying. Seriously, it's that important. So I want you to grab your notebooks, grab your pens, maybe get a strong cup of coffee, because we're going to dive deep into the specific systems that keep you on course. I'll be pointing out some guaranteed test questions along the way, so be ready to take plenty of notes. All right, let's get started. Here's our flight plan for today. First up, ground-based navigation, specifically the VOR. Second, we'll cover classic navigation and distance tools like the NDB, ADF, and DME. Third, we're looking at satellite navigation with GPS. Fourth, radar and transponders. And finally, we'll wrap up with VFR radar services. Let's launch right in. Section 1, ground-based navigation, VOR, which stands for Very High Frequency Omnidirectional Range.
Okay, so the VOR is a true staple of ground-based navigation. You're going to use this a lot. Before we look at the instrument itself, let's talk about how it actually works. A VOR ground station is oriented to magnetic north, and it transmits azimuth information. This provides 360 distinct courses, or radials as we call them, that you can fly either to or from the station. Definitely write down this frequency range. VORs operate between 108.0 and 117.95 MHz. The way it works is pretty clever. The station sends out a reference signal in all directions at the exact same time, along with a variable signal that changes depending on the specific radial. Your aircraft's receiver simply measures the phase difference between those two signals to pinpoint your exact radial. It's like a giant invisible compass rose in the sky. Now, looking at the standard VOR indicator you'll see in the cockpit. Your aircraft uses a V-shaped antenna to feed the receiver, displaying the information right here on this dial. Let's break down the components. Down on the bottom left, you have the OBS, the omni-bearing selector knob. You turn this little guy to choose your desired course, which then shows up at the top course index. Right in the center, we have the CDI, the course deviation indicator needle. If you start to drift off your chosen course, that CDI needle is going to deflect to the side. Write this rule down for your exams. On a standard round gauge, just like this one, a 1-dot deflection equals a 2-degree course deviation. Finally, you've got the to from indicator right in the middle, and that tells you whether the course you've selected will take you toward the station or away from it.
So how do we use this practically when we're up in the air? I want you to write down this acronym in big, bold letters: TINGO. TINGO. This is your absolute standard operating procedure for basic VOR navigation. Step 1, tune. Put the correct VOR frequency into your radio. Step 2, and I cannot stress this enough, is the most critical: identify. Before you ever trust a VOR signal to guide your airplane, you must identify it by listening to the Morse code or the voice identifier. If you don't hear code, or if you hear the Morse code spelling out the word TEST, do not use it. That means the station is down for maintenance. Step 3, nav or GPS. Just ensure your source mode is properly set to nav. And step 4, OBS select. Turn that OBS knob until the CDI needle centers with a from indication so you can determine your current orientation. Now, while VORs are fantastic tools, they aren't perfect. There are 5 main errors you absolutely need to know, especially for your written exams. First up is line of sight. Because the VOR uses a VHF radio wave, there has to be a clear, unobstructed path between you and the station. If there's a mountain in the way, you lose the signal. Second is the cone of confusion. When you fly directly over the station, within about 1 nautical mile, that CDI needle might start swinging wildly. The crucial thing to remember here is, during station passage, ignore those crazy deviations and simply hold your heading. Third is the zone of ambiguity. When the station is exactly 90 degrees perpendicular to your course, the instrument gets confused and displays a red flag. Fourth is a weird one: propeller modulation. A certain propeller RPM setting can actually interfere with the signal and cause up to 6 degrees of error. And finally, reverse sensing. This is pilot error. If you set the wrong OBS setting, say you're flying to the station but you have a from indication dialed in, the needle will deflect in the opposite direction of where you need to go. Because VORs are so critical for instrument flying, the FAA requires regular checks under FAR 91.171. This is a classic check ride topic, folks, so please memorize these tolerances. If you're doing a ground check or a VOT check, the maximum allowable error is plus or minus 4 degrees. However, if you're already flying and doing an airborne check, the tolerance is a little bit looser, at plus or minus 6 degrees. Oh, and one more trick to jot down: If your plane happens to have dual VOR receivers, you can just tune them both to the same station. To pass the check, they must read within 4 degrees of one another. Section 2. NDB, ADF, and DME. Let's look at some of the more classic navigation and distance measuring tools. All right, let's step back in time a little bit and break down the NDB, or non-directional radio beacon. This is an older ground station that operates on lower frequencies between 190 and 535 kilohertz. It basically just transmits raw radio energy out in all directions. To use it, your aircraft needs an ADF, an automatic direction finder. The ADF is pretty smart. It combines signals from a sense antenna and a directional loop antenna. And the result is that a needle on your dash simply points directly to the ground station. However, because NDBs use those lower frequency radio waves, they are highly susceptible to environmental interference. You'll want to jot these errors down. First, precipitation static from flying through heavy rain or snow can disrupt the signal. Second is the shoreline effect, where radio waves actually refract or bend as they pass over water and hit the coastline. Third, lightning. This one is wild. The ADF needle is drawn to electrical storms, meaning it might literally point at a thunderstorm instead of your navigation station. Fourth is the twilight effect, which causes needle fluctuations during dawn and dusk as the ionosphere shifts. And lastly, the terrain effect, where mountains with high metal deposits can reflect the radio waves and give you false readings. When you're navigating with NDBs, you need to understand a little bit of math. The ADF indicator in your panel gives you what's called a relative bearing, or RB. This is simply the station's position in relation to your aircraft's nose. If the needle is pointing straight ahead, the relative bearing is 0. But to actually navigate on a map, what you usually need is the magnetic bearing, or MB. That's the station's position in relation to magnetic north. You need to memorize this formula. Magnetic heading plus relative bearing equals magnetic bearing. MH plus RB equals MB. If your airplane has a fixed card bearing indicator where 0 is always permanently stuck at the top, you are going to be using this formula a lot. Now, knowing what direction to fly is great, but let's talk about knowing exactly how far away you are. That's where DME, or distance measuring equipment, comes in. Operating between 960 and 1215 megahertz, DME gives you your distance in nautical miles. It does this by computing the precise time it takes for a signal to bounce between your plane and the ground station. But here is the big catch you need to remember: slant range error. DME reads the diagonal distance from your plane down to the station, not the true horizontal ground distance. Think of it like the hypotenuse of a right triangle. This error gets much, much worse the higher you fly and the closer you get to the beacon. To put that into perspective, if you fly directly over a DME station at exactly 6,076 feet above it, your DME will read exactly 1 nautical mile, even though your actual horizontal distance to the station is 0. Section 3. Satellite Nav, GPS, and RAIM. Let's step out of the past and into the modern era with the Global Positioning System. GPS is a total game changer. It provides incredibly accurate position, velocity, and exact time information. It works using triangulation. The system calculates the precise fraction of a second it takes for signals to travel from multiple satellites orbiting the Earth down to your receiver, pinpointing your exact location in 3-dimensional space. The entire GPS architecture is broken down into 3 major components, and you should definitely write these down. Number 1 is the space segment. This consists of 24 Navstar satellites, plus a few backups, arranged in specific orbits so that a minimum of 5 satellites are always in view from anywhere on the globe. Number 2 is the user segment. Well, that's us. It's our aircraft antennas and the receivers in the panel. And number 3 is the control segment. This is a network of ground-based monitor stations and uplink antennas that constantly track the satellites. They ensure the orbital positions and the internal atomic clocks on those satellites remain perfectly, flawlessly accurate. Now, because we rely so heavily on GPS, especially when shooting critical instrument approaches in bad weather, we need to know beyond a shadow of a doubt that those signals are trustworthy. You can't just blindly trust the screen. Enter RAIM, Receiver Autonomous Integrity Monitoring. RAIM is essentially software that built right into your GPS receiver that constantly checks the health and accuracy of the satellite calculations. If a satellite starts acting up and sending bad data, RAIM isolates that signal and ignores it, keeping you safe. But to do this mathematical cross-checking, RAIM requires a minimum of 5 satellites in view. Always, always remember to check your GPS NOTAMs during your pre-flight briefing to ensure RAIM will be available for your specific route and time of flight. Here is something super cool about GPS that's completely different from flying a VOR. With a VOR, the course width narrows physically as you get closer to the station, like the tip of a slice of pie. But GPS CDI sensitivity automatically changes based on your phase of flight. When you're cruising along en route, meaning you are further than 30 nautical miles from your destination, a full-scale CDI deflection represents 2.0 nautical miles off course. As you cross that 30-mile boundary, the GPS knows you're getting closer, so it enters terminal mode, tightening the sensitivity. Now, a full-scale deflection means you're only 1.0 nautical mile off course. Finally, 2 nautical miles before your final approach fix, the GPS shifts into approach mode, tightening drastically down to just 0.3 nautical miles. It's automatically funneling you in for a precise landing.
Section 4. Radar and transponders. We've talked extensively about how you navigate the skies, but how does air traffic control navigate you?
The word radar literally stands for radio, direction, and ranging. ATC uses electromagnetic waves to identify your range, altitude, direction, and speed. But it's important to know that it operates using 2 very different technologies. The base level is primary radar. This is an older, ground-based system that transmits a narrow, powerful beam of raw radio waves that literally strike the metal of your aircraft and bounce back to the dish. However, primary radar has some big limitations. It struggles with ground clutter, like bouncing off mountains or heavy weather. And more importantly, it can't easily identify exactly who you are or what altitude you're flying at. To overcome this, the system uses secondary surveillance radar. Instead of just bouncing raw waves off your fuselage, the ground station sends an interrogator signal. This signal essentially asks your aircraft's transponder to reply. Your transponder then sends a smart, coded message back down to ATC, giving them your specific ID and your exact altitude. It's a digital handshake. And that brings us perfectly to the transponder itself. It uses a 4-digit squawk code, using only the numbers 0 through 7. That math gives us 4,096 possible codes to use. There are a few different modes of operation you must understand for your tests. Mode A simply transmits that 4-digit code to ATC, but it offers absolutely no altitude reporting. Mode C is much more advanced, and it's critical for flying in controlled airspace. It transmits your 4-digit code plus your pressure altitude. Finally, Mode S does everything Mode C does, but it also allows aircraft to digitally interact with each other for advanced traffic avoidance systems.
Section 5. VFR radar services. Let's look at flight following and how ATC can assist you day to day.
Just because you are flying visual flight rules on a beautiful, clear day doesn't mean you have to be totally alone out there. You can request flight following, which is a really helpful radar traffic information service. When ATC spots another aircraft getting near you, they will alert you over the radio using clock directions relative to your current track. For example, they might say, traffic, 2 o'clock, 5 miles, 4,500 feet. Knowing exactly how to reply is crucial radio etiquette. If you scan the sky and spot the aircraft, simply key the mic and say, traffic in sight. If you look and cannot find them, say, negative contact. And here is a massive pro tip you should absolutely underline in your notes. ATC is giving you the traffic's clock position based on your ground track as seen on their radar screen. Therefore, if you are flying with a heavy crab angle to correct for a strong crosswind, ATC's 12 o'clock might actually be at your 1 o'clock or 11 o'clock, looking out the windshield. You always have to compensate for your wind correction angle when scanning for that traffic. I want to leave you with this final, vital thought. We've talked about some incredible technology in this explainer today. Everything from VORs to atomic clock satellites orbiting 11,000 miles in space to advanced radar transponders. But the absolutely crucial point is this quote, taken right out of the manual. Although the aircraft gets traffic alert service, the pilot has responsibility for see and avoid. Never ever let amazing technology make you complacent in the cockpit. ATC is a fantastic backup, and GPS is a miracle, but as the pilot in command, your 2 eyes looking outside that windshield remain the ultimate collision avoidance system. So as you prep for your very next flight, ask yourself, are you relying just a little too much on the screens inside, or are you truly scanning the skies outside? Stay vigilant out there, future pilots. Thanks so much for joining me on this explainer. Study hard, and I will see you next time.